4. Yeah, what fields? Whereabouts are we now?
4.
Ah!
This lecture 4, I think.
Oh no! Oops, what did I do? No, I just dropped it into the folder. Right. Oops. Okay. That's better. We did this one?
Yeah.
Ah!
Oh, again.
Where did it go into?
I think 5. Lecture 5.
Yeah.
Oh, yeah.
Right, which one are we on? 4. Good, alright. Let's not cause any more problems. Magnetic fields now. Big enough lecture actually today. Magnetic fields. Can you write this down, please? You're awake today? You have the right amount of sleep? Yes? Okay. Right, magnetic fields. You got that?
Yes.
Bruce? Yep. Okay. So it's a good bit to do here. Alright, so a magnet. You all know these from your childhood. And you know that it has 2 parts, a north and a south. So what exactly is the magnetic field? Well, that's the area around a magnet in which there's the magnetic force. That's basic. Well, there's more here, but just for your basic definition, I think this is all you need. Wow. Yeah, there's a lot of vocabulary in this definition, but the first thing is just the magnetic field. It's just the area around the magnet where there's the force.
Is it similar with electric field?
Yeah, very similar. Very similar. Okay, next. So, there's actually something interesting that happens here. When an electric charge moves, it can make a magnetic field. So if you have like a little positive charge and it starts to move, it actually makes a magnetic field around itself as it moves. And this is quite interesting because it only has this field when it's moving. So if I have a charge here, no magnetic field. But as soon as it starts to move, it makes a magnetic field around itself. That's a very important and interesting result about charges. So last time we were talking about electric fields, electric field strength, electric field potential, and now we've just learned that an electric charge actually can make a magnetic field simply by moving. It produces one. Very, like you would not have thought it could just do that while it's moving. So it's not part of the definition really, but I think it's worth making a note. Moving charges make magnetic fields.
Then we can in the circle we can find the magnetic field.
In the what?
Circle.
What circle?
Circle. Like electric circle.
Oh, circuit.
Yeah, circuit.
Yes, we'll do that later. It's true. Okay, got that part?
Yeah.
Now, a bit more vocabulary. part of the hard, what makes fields hard for students is the vocabulary, especially all this new vocabulary today. So we have something else now. We have something called magnetic fields can be seen with what's called the flux lines. And the flux lines show the direction of the magnetic field. So just before you, well, I don't guess you don't have to write that down, but I do want you to understand what these flux lines are. So if I have a magnet, there's north, there's south, and this is the magnetic field. Well, I won't draw all of it because I'm sure I have a picture of it, but I'm sure you've seen this actually in middle school even. You know what I mean? This picture here. These are called flux lines, and they basically show the magnetic field. So they're kind of a little bit like force, a little bit like electric field lines. It's certainly a vector field. These are the flux lines.
How many flux lines is there?
That's also important. I've not drawn everything here. There should be maybe a little bit more, you know. Make note about this vocabulary, flux lines. You can write or you can draw, whichever works best for your notes.
Then the one like the dipole, the positive and negative charge between them, that's not flux line.
Yeah, that's I mean it almost looks like the same thing, doesn't it? But that's an electric field. But you're realizing this kind of looks like the positive negative dipole. It's very similar. In fact, when you study this chapter in more details at university, you'll discover why it's so similar. What are you doing next year? Computer science, is it? What area?
Engineering.
Okay. Yeah, so you might study more about magnetic fields then. Okay, do you have this? Yeah. Continue. So. Here's a nice picture. So, this is a bar magnet and these are the flux lines. In fact, it's common enough in the exam that they ask you to draw this.
Draw this.
Yes, that's what I said, yeah. Draw the magnetic field on a bar magnet. Now, if you have it drawn already from my one, that's fine, although maybe you should add in a few more lines. But you will need to know this diagram for the exam. It's not that difficult. The key thing to remember is that the flux lines, they go from north to south. That's the key thing to remember. Maybe you even want to write that down, north to south, help you remember. Yeah, you draw this? Can I see? Is it beautiful? Is it beautiful? It's okay. It's okay. Oh, come on, Wookie, draw some more lines in.
Does you know?
You got yours drawn? And the vocabulary here, this is called a bar magnet. Okay. Got this? Yeah? Got this? Yeah? Continue, so. Yeah. Now, inside the Earth, there actually is like a giant magnet. And I think you know this. If you remember, you have your little compass which shows you which way is north. I'm sure you've had these as a kid, yeah? These little compass. Can you give that back to her? What did she drop? Have you got it? So anyways, the reason these little compasses work is because there's a magnetic field around the Earth. And you can draw it. I'll draw it here for you. Well, should make the Earth a blue colour. Okay, and we'll put the equator here. And we are, let's say, here. Yes, sir. Now, up here is north, where Santa lives, and here is south. So you might think the magnet is like this. This side is north and this side is south. Actually, it tricks people. This is the south side of the magnet and this is the north side. And the reason for this, if you think about it, you realize, oh, it has to be this, because if you have your little compass, you know, your little compass has a little magnet. So I'll kind of draw someone standing here on the Earth. Their little magnet has a north and a south on it. So we kind of need the top to be south so that the north points up. Because you know magnets, you know all this, the north and the south, they attract. So although it's called the North Pole, it's actually the south end of the bar magnet, the imaginary bar magnet that's there. So the magnetic field around the Earth goes like this, and just like the bar magnet, it loops around. Yeah, and this is another diagram that they might ask you in the exam. So if you want to just draw it around like that, here it is here. Just remember that it's the south one up the top here and the north one down here. And I should also tell you, usually red represents north and white represents south if you colour a magnet. Yeah. You might remember this from your little compass. The north is red and the south is white. I think you all know this, or maybe can remember this. What actually makes the Earth's magnet? Like, what is inside the Earth that is making the magnet?
Inside Earth.
Do you know?
Iron.
Yeah, it's the iron inside the Earth. Iron, yeah. Now, what's very interesting is that this magnet is iron, is actually a liquid, not a solid. And in fact, believe it or not, that this magnet can sometimes turn upside down. Means the north swaps with the south and the south swaps with the north. This happens about every, I can't remember, maybe every like 20,000 years. It swaps.
This means the Earth is soft.
No, just the magnet.
Magnet is soft.
Magnet. So your little compass will then flip around.
Oh.
Happens, I think, every like 20,000 years or something like this.
When that
How
happens,
then?
they change the.
Yeah.
Well, it hasn't happened while humans have been around. Well, actually, no, I don't think so. Anyways, you see, the reason we know that this happens, you know, when you have a volcano, the lava spews out the top. The lava can sometimes turn into a magnet simply because of the Earth's magnetic field. So, you know, like if you picture like this is the lava that's coming down, and as it comes down, it cools, and then it becomes hard. But if the magnetic field is pointing this way, then actually the lava will have a small magnetic field pointing that way as well. It's kind of it's almost like the magnetic field prints onto the lava. And there's actually at least one place I know of in the Earth where when the volcano was erupting, the Earth's magnetic field must have been in the middle of changing, because at the top it points this way, but then by the time it gets to the bottom, the magnetic field in the lava is pointing the other way. So, huh? Oh, because if it has a small magnetic field inside of it, you can just like put your compass on top of the lava, and inside of it, yeah. And as you move the compass down the hillside, you'll see it starts to turn. So as it was cooling, as it was coming down, it was at the same time the Earth's magnetic field was flipping around. So that's probably like, you're probably talking like maybe 6 or 7 days the magnet was turning around. And then it will stay for maybe 20,000 years and turn back.
2,000 years.
20,000, I think.
We can check it.
Well, some people think it might actually happen soon.
Happen soon?
Might. Now, what's soon? Soon could be 200 years, so you probably will be, not around. Okay, you got this? Yeah. Next, now. So, as Wookie was actually realizing earlier, if you have a current, like in a circuit, the charge that moves actually makes a magnetic field. What does the magnetic field look like? Well, if you have a few compasses, you can actually check what it looks like. If you put your compasses around this current, what's off, then all of these will just point to Santa in the North Pole. But then when you turn the current on, they all point around in a circle. So what's actually happening here is you get this magnetic field around the moving charge. So you remember I said as the charge moves, there's a magnetic field around it. You can actually see it here. As the charge moves up, you get this magnetic field around it moving up. Yeah. I would like you to draw this picture. It's a very simple experiment to show that the current produces a magnetic field.
The more charges, the more magnetic field.
Yeah. Yes.
More magnetic field means stronger?
Well, we haven't talked about like strength and things like that yet. Got this? Yeah. Got this? Yeah. Continue. Okay. So, you can actually use this to actually make a magnet. Something which is called a solenoid. Now, it's actually. Why did I make this picture so small? I should really use a bigger picture. Let me actually zoom in on the picture. Which one is it? Could it be this one? Looks like it could be. So the idea is you have your copper wire. Whoa, there we go. zoom in a bit. Okay, you can see that okay? So, you have your copper wire, and you wrap your copper wire in a coil like this, and then you pass a current through it. So the current comes along, current goes along here, and then current leaves, and you actually make a magnetic field. But what's interesting is the magnetic field you make here looks exactly like a bar magnet. So it's like this is the north and this is the south. It has the same basic shape. So you can actually use just a piece of copper wrapped up, and then you turn the current on, and you've just made a bar magnet. And of course, this is useful. Why do you think it might be useful to have a magnet that you can turn on and off? Why might that be useful? Like, why not just use a bar magnet? Why actually use something that you can turn on and off?
We can control that. We can.
Yeah, but why would that be useful? What would be an example? Yeah, but like, give me an example of why you might want to do that.
In real life.
Yeah.
Yeah.
Or movies.
Turn on the switch.
Oh yeah, there's that thing, the relay switch. Well, just think about it as like a junkyard. You know, you lift the car up with the magnet, then you turn the magnet off and you drop the car. Something like this. So this is called a solenoid. It's when you use a copper or something like this conductor to produce a magnetic field. I should actually say often what's inside here is not empty space. In fact, if you put some iron inside of here, you actually make it more efficient. But you don't need anything in here. You can actually just have the copper wire wrapped up, but it actually works a lot better if you have a piece of iron in here. But technically a solenoid is just this. So, could you try your best to draw this? Again, this is something they could ask you to draw in the exam. Draw a solenoid.
Oh my god.
Yeah, I know.
Let's draw.
The way current is coming out is not.
It's coming out here and going in here.
Which one is first? Out is first, in is first.
This end is in.
In is first.
Well, in is on the right in my picture.
If we change the direction of the current, then
Yeah.
change it too.
Yeah. In the exam, they don't. I don't think they really care. They just want you to draw an example. Okay, you drew this. You drew this.
Yep.
Continue. Okay. Where are we? Okay. I don't know why I made that so small. What's it called? Solenoid. Let's make it there. Right. So we saw two things that we may need to clear up. There's actually a rule here to help you remember which way the magnetic field will move when you have a current. It's called the right-hand rule. So let's imagine that this is our current, and let's imagine the current is going up, for example. What you do, you hold the current, so to speak, with your thumb pointing in the direction of the current. Then your fingers here is the direction of the magnetic field. So the magnetic field is going around this way. If I turn the current to go down, like this, then the magnetic field is going around this way. Okay, so this is called the right-hand rule. And you can draw it.
Draw it.
Draw it. Yes.
It's like art time.
It is art, it's colouring time, playtime.
How could I draw it then?
Of course you can.
Okay, let's see.
You should be happy you're not in biology anymore. They'll have you drawn every day. That's all you do in biology. Draw pictures. Write blah blah blah. That's all.
Boring.
Also boring. It doesn't have to be perfect, just so you can remember the rule in your notebook. There we go.
Good.
Ah, wonderful.
Alright.
You drew it? Show me. Show me. It's alright. Bruce? You drew it?
I tried to do it.
Okay. Shamsa? Show me. That's okay. Alright. This is called the right hand rule.
I thought it's too big.
Oh, that's fine. It's fine. I'll stop. Leave it alone. It's fine.
Too long.
It still works if you had 3 fingers or
No.
2 fingers.
So
You don't have to
terrible.
worry that you have the right number. Alright, continue. Yep. So, that is for the current moving in a straight line, and then when it moves in that spiral, that's called a solenoid. So the definition of a solenoid is a coil wound in a tightly packed helix. What the heck is that? Well, do you know this verb wound? It means to turn like this. And helix is the name of this shape in maths. This is called a helix.
String?
It's kind of like this. The famous one you all should know is what's called the double helix. Former biology students, what's the double helix? Do you know? Which one?
Like tick 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 tick.
What's it called? Maybe this? Yeah. Yeah. It's the one. Oh, it's going to be hard to draw, but you have 2 of them.
Double helix.
Oh, can I even do it? Can I even do it? No, I can't even do it. It's the 2 together.
Yeah.
The DNA, yeah. So you can have a single helix and a double helix. It's the name of the shape. Okay, so you can write this down. It's like a spring, isn't it? Huh? Continue. So, we've talked a little bit about the shape. Now, you realise so far we've actually not said anything about the units. So we need a way to measure how strong the magnetic field is. And before we do that, we'll have to define exactly what we're measuring. So when we talk about the magnetic flux, and this is the symbol, for a particular part of the space, so for example, let's say I have a magnet here, north, south, and goes around like that, as you know. Like this. Imagine I'm here, and I'm looking at this part of space, and I want to know how strong the magnet is there. We call that the magnetic flux, and simply it's the number of magnetic field lines passing through the area. So here I would say the magnetic flux for this part of space, let me just call this part OR. So the magnetic flux at OR, that would equal, in my picture here, 3. And the unit is called the Weber. So I say it's 3 WB. Now this is the simplest definition I could find. In fact, the true definition is extremely advanced and technical, involving integration and calculus, if you can believe that. So this is the simplest definition I could find. Simply put, the magnetic flux is the number of field lines, and we use the Weber to count. So this would be 1, 2, 3 Webers, 3 field lines. And you notice that the definition depends on where you are. So like if I was here, looking at this part of space, what's the flux here?
1.
That would only be 1 Weber. And if I was over here, maybe 0 Webers. So it depends on your location, okay? Right, so, oh, and interestingly, the Weber is the same unit as the volt second. You can actually show that later. Volt second, yeah.
The definition we need to include over a particular area of space.
Yeah, because it is the flux is dependent on what part of space you're looking at. It's not a point.
What's the name of this symbol?
Ah, does anyone know the name of this Greek letter? Not omega.
Is it a
Not
pi?
omega. Not pi. Phi.
Yeah, phi.
No, PHI. Phi.
Phi
Hmm.
and phi.
It's the Green Lantern symbol. You know? You all know who Green Lantern is, don't you? You don't? Really?
Great what?
Green Lantern.
What's
Green
that?
land.
Greenland.
Lantern.
Yeah.
Oh. I thought you said
He's
green
this symbol, isn't he?
No, there's 2 things.
Oh yeah, but this is just the font. I know, there should be the 2 lines on the top and the bottom. Would you notice I included in mine? You have all of this? Not yet. You have all of this? Bruce? You have this? Yeah. Continue?
Yeah.
Okay. Now, next definition. The magnetic flux density, B, at a point in a magnetic field, is the amount of flux per unit area perpendicular to the field. So, again, I'll try and draw this for you. So, we imagine that we have our field, our magnetic field, and let's say this time we're here, and we're only looking at a point. Okay, what we do is we draw a plane which is a unit area. So if we're using meters, that would make it 1 meter squared. So the magnetic flux density is just the number of field lines per area. And we usually put this perpendicular to the field at right angles. So the magnetic flux at a particular point is the flux per unit area perpendicular to the field. The unit is called the Tesla, which is just 1 Weber per meter squared. Mathematically, it's this.
Tesla.
Yes?
Car company name.
Yes? Same person.
Same person? This person?
Tesla's a person.
The CEO is the name of CEO?
No, the CEO Tesla is, what's his name? Elon Musk, isn't it?
Ah, yeah.
Did you write that down? Yeah. So what is this kind of like? It's a little bit like kind of like pressure nearly, because you divide by area. Yeah. And just so you know, the B is the nearest thing we have which is like the E in electric fields. So the B is like the E for electric fields. It's not quite the same, of course, but it's like it.
Why density have no volume? Why the density have no volume? It's a density, why is it area and volume?
Oh, why is it not called magnetic flux area? Yeah, English, huh? I think it's because density is actually more general than just 3 dimensions. You can use density in 2, 3, any number of dimensions. So I think it's because density is more general than you think, actually. Okay, continue. Yep. So a moving charge produces a magnetic field. And by using the right-hand rule, we can know what the field looks like. So if the charge is moving to the right, the magnetic field is going around like this. But if the moving charge is moving in a magnetic field, it will feel a force. I mean, think about it. If I have 2 magnets, and I put them close to each other, they'll either pull together or push away. Yeah? So if I have a big magnetic field, and then inside of it I have a charge that moves, it's going to make a magnetic field. So what do you think will happen if I have a magnetic field inside another magnetic field? It will feel a force. So the question now is, if my charge moves in the magnetic field, how much force will it feel? Because remember, north repels north, south repels south, and all that. So anyway, the force F on a charge Q in a field of flux density B while moving at velocity V is, so I'll just draw that. If you have let's say you have a big magnet here, north, south, going like this, or something like that. And then you have a charge going across like this, let's say a little proton or something. From the right hand rule, it will make a little magnetic field around itself. So when it comes to here, the two magnetic fields will cause a force. Maybe it gets pushed away, something like this. How much force will it feel? Well, it's QV times B, and this is a special multiplication which I'll explain. So the force on the Q will be QV times B. The Q is its charge, the V is its velocity, and the B is the magnetic flux density. So you were asking me, does more charge mean stronger? It does, it makes more force on it. But in fact, if it moves faster, that will make more force on it. Got that?
What do you mean by this?
I'll have to explain it, yeah. Because this V is velocity, and velocity is a vector. And this B is the flux density, and that's actually a vector as well. So how do we multiply two vectors? Well, we use something called Fleming's left-hand rule, which I'll show you on the next slide.
Vector by vector.
Vector by vector, yeah. Can I go to the next slide? Show you Fleming's left-hand rule. So, this is how it works. Using your left hand, you put this finger in the direction of the field. So let's just say, we'll keep it easy. Let's say there's a big magnetic field in this room, and it's going towards the door. So that's from what do you say, north to south, isn't it?
Yeah.
So let's say that's the north end of the magnet, that's the south end, or the magnet's on the ground or whatever. So the field is going, let's say, that way. Yeah? So left hand rule, I point the field in this direction here. Okay? Now this one here is the direction of the current. So imagine I have a current or a charge, and the charge is moving towards you. It's moving this way. So it will feel a force, and the force is this direction. So if the magnetic field is going this way, and the current is moving towards you, it will get pushed up. That's how it responds.
This is not
This is the direction of the field. You point it in the same direction as the field. So like, I have one of my pictures. Oh, come on. Here. No. There. Yeah, so like in this picture here, well, I can't quite see it, but this is pointing to the right. So in this picture here, I put this finger this way. If there was a current that was moving, imagine behind the TV, and it went through here and was moving towards you, then that current would feel a force that would make it go up then. This is using the left-hand rule. Yeah? We got the idea?
But what is it? That's right.
This is left.
Left and right hand rule.
Yeah, there's two different rules.
Different?
Yes. Your left hand is different to your right hand.
I don't.
Oh, good. I didn't see you weren't doing biology anymore, so I didn't know if you knew that. Let's go back. Fleming's left-hand rule. Do we understand how this rule works? Yeah? So right hand is for when you have a current moving this way. Put your right hand around it, so the magnetic field is going around like this. And then use your left hand when this current is inside of a big magnetic field and you want to know which way the force will be on it. Alright.
Yeah.
Draw.
Drawing.
Draw it.
Oh my god. Oh.
You can do it.
Mm.
Fleming. Did you draw this? Show me. What does it look like? Where? Ah, cheater. No fingers. How are you supposed to remember this?
Label the line come.
Oh, did you? Oh, okay. Oh, the duck.
Yeah.
The duck. Quack.
For sure.
You drew it?
Yeah.
Show me.
I just tried 3 fingers.
That's okay.
Not hand.
Where? Point. Ah, that's fine. Alright, continue. Huh?
What do you mean by thrust or motion?
Oh, the force, yeah. No, thrust is another word for force.
And
Yeah.
motion is about velocity.
Yeah. It would be forced to move in that direction. There'd be a force pushing it that direction. Continue. So, next. Some questions now. A bar magnet has a flux of 2 Webers at some region in space. The region is a circle of radius 1 centimeter. What is the flux density in Tesla? I think you can do this one. Which formula do we need here?
B equals log over area.
B equals flux over area. Density equals flux over area. So try this, and I'll put the answer on the calculator now. Let me just open up the calculator. Okay, try this one. Calculate, please. Got an answer there? What you guess? You got an answer, Bruce? Let's see. Where's my cat? Here we go. Right, so what do we have on the top? 2. And on the bottom?
Pi r squared.
Pi or squared. The circle. See there, Bruce? And the radius?
0.01.
Yeah.
I should change to meter.
Yeah. So the answer is 6,366 Tesla. Yeah, did you get that? Yeah. Okay, next example now. Let's see what's next. A proton moves towards the east in the Earth's magnetic field. what direction is the force due to the field? Okay, so this is using your left hand. I'll let you think about it. A proton moves towards Mecca. That can help you picture it, right?
They mean
It's over in the east, isn't it?
Korean.
Huh?
The Middle East.
Easterly, then. So the proton is moving to the east. What way will the force be on it? So, let's try and... Which way are we pointing out here? Is that south?
That's the south. This way.
South is south.
Oh yeah, but I mean if we're standing here, like with a compass, which way is south?
South.
That can't both be north and south. That's south, isn't it? That's south. How do you know? Can't you just tell? It's the mountains. Well, it can't be east because there's no mountains and oceans, right?
You can see the
Yeah.
south west.
Yeah, but maybe the
West.
ocean is like right behind.
What?
The ocean is behind. Why not? Why?
Because I know on the east coast of Ireland there's no large mountains on the coastline.
So you have to know that to know it.
Local knowledge, yeah. So I think that must be south. So if that's south, that has to be north. Yeah.
How do you know if that's north or
That is
south?
south. Thank you for confirming that.
How do you know that's north or south? Mountain.
Yeah.
It can be then west or north.
The mountains to the west are quite far away. I don't think you can see them.
The north has no mountain at all?
I don't.
Let's check.
I don't understand why she's so. What's so confusing?
How do you know? By looking outside.
It's not south.
How?
Can't you tell that looks
Oh.
south?
Yeah, full map.
South is this.
No, without. He even take out his phone.
Yeah, my phone can tell me which way is south. Yeah, right. You're not happy with this.
I don't get how you can do that.
It's gas.
It's a gas.
Special ability.
Special ability. Thank you, Whoopi. Okay, let's focus back here now. Right, so anyway, even if it's not south, let's just pretend it's south. And that's north, that's east, and that's west. And our proton is moving east. So the proton is coming towards you. Okay? I want you to think about which way the force will act on it.
This way.
Are you sure?
Yeah.
Okay, let's check. So,
See
this
my
is
hand.
the field.
Yeah.
Which way is the field?
This.
Is it?
This is north, this south. This one.
No, be careful now.
You want to be imaginary.
The Earth's magnetic field.
Ah. Boom, boom, boom.
Which way is it? Is the field that way or is the field that way?
Hold on. This is north, right?
Yeah, Santa is over there. Santa Claus. Over there.
Yeah, but the real man is south and the
Exactly, so you'll have to think carefully which way the field's pointing. Yeah.
This way.
I believe if you remember the picture of our Earth, okay, up the top is the South Pole, which we call north, and the field goes from north to south. So the field actually goes towards Santa Claus. Okay, so the field is that way. The proton is positive charge, is moving towards you. So that means as it moves towards you, there's a force acting up on it. So if I shoot a proton at you, it shall want to move upwards in the magnetic field. Yeah? Yes, is it okay? Yeah, so this one here upwards though. Okay. Next. If there is a next one, yeah. An electron enters a magnetic field and then experiences a deflecting force. The magnetic flux density at the location of the electron is about 250 millitesla. The electron was moving at 1/10 the speed of light. What's the acceleration of the electron? Okay, so I'll draw what's happening here. You've got a magnetic field. Let's just... oh, I should tell you this. This would be useful to know. It's kind of hard to draw the field going into the page. Like into the page. It's hard to draw. So actually the way we do it is like this. If I draw circles like this, this means into the page. And if I draw circles like this, this means out of the page. So here, this one is going in, and this one is coming out. Yeah? It's just useful. You should write this down. It's useful to help you draw.
We can use this sideways, side view.
Side view?
Yeah, like, this is in front view, this side view.
Ah, yeah, but if you only want to draw one picture.
Yeah,
No, because you might have to. No, trust me. This is.
Okay.
Trust me. Okay. Can I scroll down? So, we've got an electron, and it's moving, we'll say, to the right, and then it enters a magnetic field, and let's say the magnetic field is going towards you. So it's coming out of the page. Okay, so firstly, which way will the force be? Okay, so which way should I put this finger here? To you, yeah. And then what about the electron? Which way do I put this finger? Left or right?
left.
Left.
Yeah.
Because it's an electron, it's negative.
Yeah.
Remember we said in electricity, if an electron moves from A to B, we say the current is from B to A. You remember that?
Yeah.
Remember that? So, it means the force will be up. So it'll come along here, enters the field right here, and it'll actually cause it to move up. And it'll actually leave the field up here. And while it's in the field, there's a force. Now let's write down some information. The B is 250 millitesla, and the V, the velocity, is 1/10 the speed of light.
3 by 10.
3 by 10 to the 8.
Yeah.
So this will actually be 3 by 10 to the 7. And my question is, what is the acceleration?
Find M.
Yeah. So I think you can maybe do this. Find A. What formula do you need to use here for the force?
MA.
Yeah, and what else?
QB.
QVB. Yeah.
What? QBB.
What's QVB?
The previous.
Yeah. So,
A.
no. You'll have to use this, and of course you'll have to use this to get the A. Yeah. So can you try this? Get the A for me, please. I think you can do this. I hope you can do this.
QBB.
You're much smarter than my other physics students. I'm sure you can do this.
The current going this direction.
Yes.
Q.
You have an answer?
What are we looking at?
The thing I underlined several times.
Is that a Q or an A?
Aw, come on. You know what letter that is. It's an A. find, now how's that? Is that better? Yes, thank you. Right.
M equal 9.11 by the minus 41.
What's the point of the left-hand rule here?
The left-hand rule? The left-hand rule is what told me that it will curve up. Because just because there's a force, you also need to know what direction the force is acting. I mean, think about this. If the force was acting to the left, it would push it back out. If it's acting up, it will cause it to swing around. It's very important.
Steven, the
Yeah.
mass of electron is 9.11 by 10 to the minus 31, right?
Constant number 3 on the Casio 991 calculator.
I don't have that.
Oh, that's sad. It's very sad.
1 times 10 to the 30.
31, right?
Minus 31.
Yeah.
Yeah. Otherwise, it'd be a very big electron. Got an answer, Bruce?
What is that?
Constant number 3 on your calculator.
Is it possible you don't have that function in my calculator? I don't have it.
You started. Then you and I.
Should buy a new calculator. Did you get an answer?
1.32 times 10 to the 8.
Did you get it, Bruce? I'll show you. Look. Look, let's do it now. So, F equals MA, but F equals QVB. So that means MA equals QVB. And what am I looking for? The A. So the A is QVB over M. Right, so let's type that in. Q, guys, look please. Q is electron. Yes? The V we said is 3 times 10 to the 7. The B is 250 millitesla. And the M is constant number 3. Yeah? So the acceleration is quite large. 1.32 10 to the 18. Did you get that?
But you
What?
said the F equal QV, the special type.
Yeah, I didn't put it here because I've already considered it in my picture. The effect of it is to make it move around like this. The charge of an electron. Yeah? You look confused. What's wrong?
How show you that?
This thing? Alright, okay. This is the field. The field is moving to you. So, to you. This is the current. The current is not going right, it's going left. Because it's an electron. Yeah?
How did you know where it's north and south?
Ah, in the picture, this symbol means the field is moving to you. Out of the page.
Oh.
To you, yeah.
To me.
To the reader looking at it on the page.
Anytime north.
That you're the north end of the magnet or the south end of the magnet? You'd be the south end of the magnet because you draw the lines going from north to south. Yeah.
If we can draw that picture, you can solve this question?
You don't even need to draw the picture to solve this one. But sometimes, I'm going to give you an extra part to the question here. Part 2. What's wrong? Are you flipping me off? Part 2. This is going to move in a circle when it's in the field. I want to know the radius of this circle. And that is a very, very, very common exam question. The radius of the circle here. Very common exam question. That's what I want you to get now. Did everybody hear me? I want the radius of the circle it makes as it's in the field.
Where is the center?
Doesn't matter.
Do we need the center though?
You do. Yeah, you do. You do. If it helps, you could multiply this by m to get the force. That helps. What's wrong with you? You're trying to become one with the magnetic field, is it?
I can visualize.
Don't know. The flux density we know is 250 millitesla. You can't understand how strange you look to me. So I have this guy here and he's all and then here you're like and then she's sitting there going, screw you, teacher.
It's hard to figure out this.
What?
Can we calculate the radius or are we confused? I think you can do this. You have to remember your circular motion formulas.
So long.
Oh!
Yep.
Right?
Yeah.
Find it, right?
It's simple, yeah.
Ah, it's easy.
The one from yesterday, the M omega.
Guys, come on. If it's moving in a circle, A equals V squared over R.
We don't need to imagine, right?
No, so you have this, you also have this. So you easily get the R. Come on, wake up, give me the R now. So the R is V squared over A. 6.82 meters, yeah. Oh, it's quite a small circle, is it? Yeah, let's calculate it. V squared, 3 times 10 to the 7, isn't it?
It's not scary.
Thank you. And then, do I still have my last answer there? Maybe I do. It's not even a millimeter, it's like 0.68 millimeters.
Even you can draw that situation for us because I couldn't imagine that situation, that circle.
Oh well, it just I'm not sure what you mean. Like I've drawn it here.
Yeah.
So it just means that this is 0.68 millimeters.
Yeah.
Yeah.
Soon.
Yeah.
Right?
Yeah.
It's just then the part of circle that is.
Well, it depends how big your field is. Like if your field is only this big, you know, and it comes in and it curves around and it comes out, you know. But if your field was bigger, like if it was, you know, I don't know, like here, I guess it could come in, could even swing all the way out and come back. It depends how big the magnetic field, the area is, you know. Usually in the exam, they make it so that it makes a 1/4 turn and then it leaves the field. Normally what they do in the exam. Is this okay?
Yeah.
You all forgot this. Well, nearly all of you forgot this.
This formula is from circular motion.
Yes. Yes. Because funny. It's moving in a circle. So it would make sense to use this one. Is it okay? You're looking, I don't know, hungry and confused. Well, look, I have some questions you can feed on for a few minutes, and then you can get your break. So, so not actually like 1, 2, 3 is very quick, and number 4 is like the example I just did, where I asked you to find the radius. So, in fact, I actually think you should get these 4 done now. Shouldn't take you more than 10 minutes to do these 4. Okay? And then you can have your lunch. I'll leave this on the board for you to work on. Let me just stop the video.